Hey, we're continuing our work with random variables. Today, the big change is instead of just talking about discrete variables, we are going to focus on continuous random variables. And the goal with these ones is really just to use their probability distribution to find probabilities. So we're only calculating probabilities with these variables for now. Their distribution is modeled by a density curve. If you forgot what that meant, just kind of think about what a bell curve was when we did like the empirical rule, the 68, 95, 99.7 thing from last semester. These probabilities, we are going to be calculating intervals for these events only. So I'll just say here, we are never doing something that is exactly equal to. And I'll try to explain why. One more thing with these continuous random variables, the mean and standard deviation is already going to be given to us. We're not going to have to calculate the expected value today or try to find the standard deviation of these distributions with the variables. They'll just be given to us. So the big thing is, one example of a continuous random variable is height. For example, here is a number line representing the height of some student. So maybe he's like 67 inches tall, maybe 68 inches tall, maybe 69 or 70. So the student, we measure their height, going to fall somewhere within this number line. Now, say I measure the student's height using a tape measure or something, and I find that he's 68.3 inches tall. So typically, if that happens, you're probably just going to round down to 68, and that's how it gets reported. If I got a more accurate device to measure with, I might find that he is 68.367 inches tall. And somebody else could make that measurement and get something slightly different. So we'll never know the exact height of the student. Maybe he falls somewhere in this range, but he can always fall between two other values, which makes it continuous. So for the most part, continuous variables, they measure something, whereas discrete variables are usually the count of something, just as a general guideline. So all that being said, for probabilities, to actually calculate the probabilities, again, we don't know where this height is exactly for the students, but we can calculate the interval. So if I did height like this on the x-axis, and I've modeled the height of a student using a density curve, it's probably going to fall somewhere near the mean. We're going to get the average every time. If I were to repeatedly measure the student, I probably get pretty close to the same thing every time. Maybe sometimes the student is like tippy-toeing, he's up here in this range. Sometimes he's down here, and so on. We'll just call this x. So the height of the student, like here, we don't know exactly what this is. We will never be able to find that probability. Just for example, like 68, if we were getting around 68 every time. This, we will never do. But what we could do is calculate an interval of events. Like you could do something like this. The probability that his height is greater than 67 inches, but less than 69 inches. These are the types of questions that we're going to answer with continuous random variables. And just one more thing that I want to make clear. If you ever see, just kind of as a side note, if you ever see on a continuous random variable problem, or if you're ever asked to calculate something like this, the probability that some random variable is less than or equal to some amount, well, these probabilities are actually just areas underneath this density curve. We're literally just calculating the area between these two values to get our interval and to get our probability. So when you see exactly equal to 68, well, that is just a straight line there's no area there. So it doesn't contribute to our probability at all. Probability for continuous random variable is this stuff right here. It's the area below the curve with their corresponding values. So not the entire curve. The entire area is 1 for density curves. Okay, so again, this statement is the exact same thing as this statement. So that equal to sign there doesn't apply to a continuous random variable. So the probability that x is less than or equal to 68 is the exact same thing as the probability that x is less than 68. The equal sign doesn't matter with continuous random variables. And again, it's just because that makes a straight line exactly equal to something, which means it doesn't have any area. So we're not going to assign a probability to it. Okay, so let's look at this example problem real quick, kind of walk you through what these problems look like. Mostly going to be review, I think. So here's our situation. The weights of 3-year-old females closely follow a normal distribution with a mean of 30.7 pounds and a standard deviation of 3.6 pounds. Suppose we randomly choose a 3-year-old at random and call her weight x. So x is our random variable. It represents the weight of the child. Let me actually space these out a little bit more to get myself some more room to work. So question A, or part A of this question, what is the probability that she weighs at least 30 pounds? I think a good starting point for any continuous random variable problem or any normal distribution problem, remember that is a very key word right here, normal. That means normal distribution calculations apply. So the probability that she weighs at least 30 pounds is going to be, or again, like how I'm starting this off is just writing my statement. So I'm looking at the probability of x, our random variable, is, okay, so at least 30 pounds. At least 30 pounds. So that would mean we want her weight to be greater than 30. Again, I don't have to include the equal sign because it's a continuous random variable. We don't know what the probability is that she would be exactly 30 pounds. Put a little equal sign here. One more thing that you always want to do with normal distribution problems is sketch the curve and the area that you're trying to find. So here's our density curve. We know it's normal because it said so. Draw a little axis down here. And then, again, like I said, it was mostly going to be review. So what I would do now is list the mean like this. And the mean it gave us is 30.7. And then typically, when you draw a normal distribution curve, you go 3 standard deviations to the right. List those values, and you go 3 standard deviations to the left to get your placements even more accurate. So this is really going to help whenever the grader scores your AP exam in May. And I think it helps your problem make more sense whenever you do find the answer. So we're looking for the probability that x is greater than 30. So that would place us probably about right here, which means we're trying to find this area. So just right off the bat, we know that the area that we're trying to find is probably greater than 50%. Okay, so to do this, you have a couple of different options. To do this, you can either find a z-score, where the observation minus the mean is being divided by the standard deviation, and then look that value up in table A. There's also a function on your calculator that can do this for you. It is normal CDF. That's what I think I'll do. So to get to normal CDF, all you'd have to do is turn your calculator on, hit the stat button. Actually, not the stat button. You hit second to get to normal CDF on your calculator. You hit second, and then you can click on vars. Second vars, and you should see something there that says normal CDF. For me, it's option 2. Now, for normal CDF, you just need to input a couple things. It's asking us for the lower amount first. So for the lower amount, let's type in 30. And then it's going to ask you for the upper limit. So after typing in 30, go to the upper limit. And the upper limit is like essentially infinity. You could just type in something unreasonably high, like 100,000, and that should work out just fine. Let me actually just keep track over here. 1, 0, 0, 0, 0, 0. And then the next thing I'm doing is the mean. The mean it gave us of 30.7 pounds. I'll type that into my calculator. Scroll down to standard deviation next. The standard deviation given is 3.6. So if you go to normal CDF and just type in this information, it will give you this probability. Type this in, hit equals, or paste and then equals. It looks like we get something pretty close to 0.758. 0.758. And that's it. That's our probability. So quite a bit more than 50% actually, but oh well. 0.758. All right, fantastic. Feeling pretty good about that then. Let's move on to the next problem. Oh, I did not type in my standard deviation. That's why it seems so unreasonable. Hey, so the standard deviation is actually 3.6. I left it out as 1. All right, recalculated here. And now the answer makes more sense. Hey, and that is the benefit of drawing this distribution. That 70% looked way too high. Hey, so I redid my calculation and I actually got 0.577, which makes a lot more sense of where the 30 would go. So there's essentially like a 70% chance, or sorry, there's essentially a 57.7% chance that the baby's going to weigh at least 30 pounds. Okay, finally moving on to the next question. What is the probability that she weighs less than 32 pounds? So this one is just going in the other direction, but still do this the same way, or kind of use the same steps. We want to write our statement, the probability that the girl weighs less than 32. Again, one way we could do this is just using normal CDF, which we'll do. But before that, let's sketch our distribution. Not perfect by any means, but that's okay. What was the mean again? 32? No, 30.7. And we just go 3 to the right, 3 to the left. Okay, fantastic. So 32 would probably place us, I don't know, pretty close to like this. So maybe our solution is going to be pretty close to 60% again, because we're looking for this area. All right, so once again, you can use a z-score to do this and look that value up in table A, or you can use normal CDF. That's what I think I'm going to do. Normal CDF on the calculator. So you just start with your lower amount, which in this case is way out here, like negative infinity. So obviously the weight is never going to be below 0 pounds, but we'll just put in like negative 1,000 just to really encapsulate everything less than 32. Our upper limit this time is 32. The mean and the standard deviation haven't changed. We still have a mean of 30.7 and a standard deviation of 3.6. All right, let me get the stuff in the calculator real quick and we'll get to calculating. Lower negative 1,000, upper limit 32, not changing the mean or the standard deviation. So it looks like this time I got about 0.641. 0.641. Okay, so essentially 64% chance that that baby or that girl is going to weigh less than 32 pounds. Okay, fantastic. So this next one is going backwards, essentially. For part C, what weight places the girl in the 85th percentile? So for a question like this, we're not actually finding a probability here. We're finding the actual value. What weight places the girl in the 85th percentile? So what we're doing is not finding a probability statement this time. We're just actually using this probability or this area to find the value of x. So I'll just draw a normal distribution to hopefully make it clear what we're trying to solve for. Again, the mean is 30.6. No, 30.7. Is that what it was? 30.6, 30.7. I think it was 30.7. All right, so here's our x-axis for height. Now, 85th percentile, that's pretty far to the right. Maybe it's like way out here. So we're looking for, what is this x value? Now, there's a couple ways to do this one as well. You could use this formula for z-scores, where you find the z-score from table A, and then you solve this for x. This would give you the value that puts the person or the girl in the 85th percentile. Now, a shorter way to do this, to save you some time with multiple choice whenever you take the test, is go back to second and then bars on your calculator, and you're looking for something that says inverse norm or INV norm. We're doing an inverse calculation. We already know the area underneath the curve. The area is 0.85. What we're trying to find is the value that puts us at that percentile, or that has that area. So inverse norm is what we're looking for. And if you go to second, bars, look for inverse norm, hit enter on your calculator. It asks you for the area. So the area that we're looking for, the area is 0.85. The mean is 30.7, and the standard deviation is 3.6. Okay, now when it asks you about the tail, just think about where your value is. The area that we're looking for is left of that value. So we definitely want this to be left-tailed. Okay, so if you hit enter, you should get the value for x. Or if you paste this anyways, 0.5, the mean of 30.7, and the standard deviation of 3.6, we should all get the same things if you're working along with me here. It looks like the weight that puts the baby or the girl in this percentile of 85th percentile would be pretty close to 34.4 pounds. Again, you would get the same result if you went through table A, but calculators can just, save you some time on problems like this. All right, so hey, thanks for watching. I'll see you all in class. Bye-bye.